So quick recap of the concepts we learned in the last lecture. We discussed about free body diagram method of applying Newton's second law to any dynamical situation. And we had also discussed about tension as another type of force that acts in mechanical systems which have strings, threads, etc. So let's start with a quick recap of those concepts. So in the free body diagram method, what we had seen that if on a certain object, there are a number of forces acting. So I'm just drawing an arbitrary situation here, not any specific case. Suppose we have number of forces acting on a body. So any number of forces. And the body is, let's say, having an acceleration as a result of that in a particular direction. Then what we do is we represent the body by a particle and draw all the force vectors as vector arrows originating from that point. So we'll have to, redraw all these arrows such that they look like they're originating from that point. So that's the first step. Then we'll have to select a proper coordinate frame. Like in this case, this might be our system of axes. And according to that system of axes, we'll have to resolve the forces. So next step would be resolve forces. And third step would be apply the equation net force is equal to mass into acceleration in component form. Yes, Sanya, I will send the recording. In fact, I think I've not sent the recording in the notes of the second lecture. I will do that in just a bit of time. So you can review that also. So this is the general method. So the first step was, draw the FBD with all the force vectors. Second step is resolve the forces, and third step apply the Newton's second law in component form. So let's start with an example. This today. So now in our example, we now have this situation. We have, let's say, a cylindrical body which is placed like this. Like the junction point between two inclined planes which are perpendicular to each other. And with respect to the horizontal, this one is at an angle of 37 degrees. So a cylinder of mass, let us say 10 kg, is placed at the intersection of two perpendicular smooth surfaces, A and B. So take G equal to 10 meters per second square. Sine 37 as 3 by 5. Cos 37 as 4 by 5. And calculate the normal reaction contact force applied by each surface. Okay, so this is a review problem for us for the concept of free body diagram applications. Just start with this. So again, start this problem using the method of free body diagram that we discussed previously. Okay. Just make the FBD and try to resolve the forces. I'll discuss it in a moment. We are just the three state. Okay, so let's understand that in this situation, first of all, how to draw the free body diagram. So how many forces are acting on this body? Can anybody tell me? Total of how many forces are acting on the cylinder?
Three.
Yeah, very good. 3 forces. Okay. There is obviously the weight of the object, which is acting vertically downwards. But then there are 2 normal reactions. Okay. Now, what will be the direction of normal reaction at each contact point?
Perpendicular to the surface.
Yeah, perpendicular to the surface. So in this case, it will become pointing towards the center of the cylinder, right?
Yes, sir.
Because the surface will be like a tangent to the circle. So perpendicular to the surface will be along the radius, like this. So this is the center. So let's say this is normal reaction E, okay, and the second surface will be applying a normal reaction along this line. That will be like this. So now when I convert this force diagram into an FBD, free body diagram. So remember, I have to show the cylinder like a point mass, okay, and then show the forces acting with respect to the point mass. So this is our weight mg. So now the only thing which is slightly tricky, which we have to do next properly, is the angles. Make sure that the angles are correct. So this is Na, and this is the normal reaction applied by B. So in this case, it will make sense to take X and Y axis like this. In which case, what we have to know is how much this angle is and how much this angle is. So can you tell me how much this angle will be? The normal reaction that Na is making with the horizontal?
37.
Sorry,
Sir, 37 degrees.
37, sure.
Sir, that NA and X axis, no?
Yeah, Na and X axis. Very good.
Yes, sir, that is given, no, 37 degrees.
Actually, that is not given directly if you see beta. Thoda sa wo indirect hai because see what is happening. What is given is that this is perpendicular and this angle is 37, which means that this angle is 53. So now the normal reaction acting at a point like this is like this one. It is perpendicular to this surface. So that's how you will see that it works out to be such that this angle is 37, because this angle is 53. So again, this angle is 37. So Na is acting at 37. Now likewise, Nb is acting along a line like this. So you look at Nb. Now this angle is 53. So this angle is 37. Sorry, the other way around. Yeah, that's correct. So this angle here will be 53 degrees. Okay, so angles are clear, I hope. So now the only thing left is the resolution. So here itself, I'm going to divide this into components. So Na's X component will become Na cos 37, so 4 by 5 Na. And Y component will become Na sin 37, so 3 by 5 N. And similarly, this one's components so this one will become 3 by 5 NB. and this will be 4/5 NB. Verify that yourself. Okay. NB cos 53 is 3/5 NB. That is the x component. So now what is happening is that this object is at rest. That means its acceleration is 0. So the forces should be balancing. So the net force be equal to 0. So along the x-axis, you can see we have 4/5 NA acting along the positive direction, 3/5 NB acting along the negative direction. So this gives our first equation. And along the y-axis, we have 4/5 NB plus 3/5 NA, but minus mg. That is. So now we have to solve equation 1 and 2 to find out the value of NA and mg. Yes, that's correct, Kushi, that if we say the acceleration is 0, it means that the x component of acceleration is also 0, y component is 0, z component is 0 in general. Yes, very good. Na will come out to be 80 newtons and Nb will come out to be 60 newtons when you calculate. From this equation, you can show that Nb is 4 by 3 Na. So substitute that here. So 16 by 15 plus 3 by 5 Na. Okay. Oh, it's the other way around. This one is 60. This one is 50.
Sir, I did it with a shorter method. I directly resolved the MJ with x-axis and y-axis in diagonally, so that I get directly then I substituted MJ towards x-axis with Na and MJ with y-axis with NB. So then I got directly.
Correct. You can do that also. Okay, so I'll just illustrate that method here. So normal, actually what is happening here, in this case you can do that because these are perpendicular to each other, right? So because this happens to be 90 degrees, so fair enough, you can take this as your y-axis and this as your x-axis. Okay. Now mg can get resolved. Okay, so when we resolve mg, you can see that this angle will be 37 degrees. Sorry, this angle will be 53 degrees.
No, sir, that is 37 only.
No, see now. Acha, that is 37, correct. So you can resolve mg into the components and balance it with Na and Nb. Okay. So now let us move on with more to do with questions involving tension. So we had seen last time tension is a force that acts along the length of anything like a thread or rope or chain, etc. When it is stretched out or under tension. due to external forces. Now, the important next thing that we learn today here.
Excuse me, sir.
Yes.
Sorry, I accidentally just got disconnected.
Yeah.
For like 1 minute. Sir, after that example, this is what you've written, tension.
Which one? The previous example?
Yeah, this cylinder example. After this, you've written this only, right?
Yeah. Yeah, tell me.
Okay. Thank you.
Ajay, you want to finish writing this? Okay. So everything is clear now?
No, I just got disconnected, so I thought you went ahead.
Okay.
Okay. Got it. Thank you.
So this was the last thing we did. Right. Now, one important aspect of tension that we have to understand is that for a light thread, that means the mass of the thread is negligible. It's so small compared to the other things in the system, like the blocks, etc., that it can be neglected. So for a light thread, the tension is always uniform across it. But for a heavy rope or chain, the tension can be, but that means it's not always the case. It can be very. So let's understand this with an example. So we'll compare two different situations. One situation is where we have a heavy kind of rope that is used to suspend a heavy block vertically. So AB is a heavy rope of mass, let us say 2 kilograms, and length, let's say 5 meters. And this is a block of mass, let us say 8 kilograms. So this is one case. And the second case, we consider as a similar kind of situation. Again, I will consider a heavy rope only, but not as heavy, comparatively much lighter. So it's a much thinner gauge rope, let's say, such that this rope now has a mass of 1/10 of this, that is only 200 grams. And in turn, the weight of the block is much more now. I replace this with a heavier block. With a mass of 9.2 kgs or 9 kgs and 200 grams. Okay. And same length. Now, each of these cases we have to calculate the tensions at the two ends A and B of the rope, and also at the midpoint C of the rope. For each of the cases, calculate tension at A, B, and C, C being the midpoint. Take G as 10 meters per second square. Okay, so through this example, we'll also understand the justification for the above statement that heavy ropes or heavy chains can have variable tension, but if the chain, if the string is massless or light, okay, sometimes light strings are also called massless. So nothing is perfectly massless, of course. Nothing can have zero mass. But if the mass is so small that we can neglect it, So like, let's say we had a situation where the block is like this in kgs, but the mass of the string attached to it is only in a few grams or few milligrams even. Then compared to the weight of the block, the weight of the rope is going to be negligible. So we can say that effectively it is massless. That is what we mean by the term massless, massless thread or massless rope, etc.
So वो m is equal to क्या लिखा है?
2 kgs below the heavy rope, na? The heavy rope is 2 kgs and the mass of the block is 8 kilograms. Second case, the rope is 0.2 kgs and the block
No
is
sir,
9.
block का पूछा मैंने.
अच्छा, block का first case में ना
Yes sir.
8 kgs. Okay, I'm checking the answers, people. There has to be some calculation mistakes. Okay. Yes, Rishita, your answer is correct. So maybe some of you, this value is not clearly written here, so I'm just rewriting it. 8 kgs I've taken. So in the first case, if you start with the free body diagram of the block, you can see that on the block, whatever force will act, that is the tension at the point B, and that will balance the weight of the block. So tension at the point B will be, if the block is at rest, its acceleration is 0. So that will be 80 newtons. Now, if you see the situation of the rope, I draw the complete rope. I mean, ideally, I should draw an FBD just like a particle, but here for demonstration purpose, I'm sure like this. So this and this you can see are an action reaction pair, okay? And the rope's own weight will act through its center, and that will be equal to 20 newtons. So the rope is also at rest. For the rope, we'll have the equation TA is balancing TB plus its weight. Yes, very good, Rishita, that's correct. Okay. Now, for this part, for the tension at the point C, what we can do is we can make an FBD, for example, of the section BC of the rope. So it's of L/2 length. So the tension at the point B we already calculated from here. It was 80 newtons. Okay. The tension at the point C is unknown. But now the weight of this section of the rope is half the length. So the mass will be m/2. So we have TC has to balance the sum of these two forces. Now, if you do the same kind of situation in the second case, you'll see that parametrically the values will come out to be the same. That will make this 92 newtons.
Sir, what was the weight of the rope in the second case?
The mass of the rope is given to us as 2 kgs. Okay. Acha, in the second case, in the second example, the mass of the block was 9.2 kg and the mass of the rope was 800 grams or 0.8 kg. Okay. So same FBDs as the above case, but just the values are different. So now you can also imagine a third case where suppose we had capital M almost equal to 10 kg, slightly less, and small m is tending to 0, is negligible. Then tension at all the 3 points would be equal. Yeah, so for tension at the point C, Khushi, what we've done is we made the FBD of half the rope, this part. This is the free body diagram of that to the section CB, the lower half of the rope.
So that's the continuation for the third one, right?
Yes. So if you had a third case where the mass of the block was almost 10 kgs, slightly less maybe, but the mass of the rope is almost 0. It's just a few grams, let's say. So then in that situation, the rope having a negligible mass, the tension at all 3 points would be same. And more or less the string would have uniform tension at all points. Okay, so hope this example is clear to all of you.
So just 1 minute.
Okay. Okay, so done, I hope.
Sir, almost done. Give 1 minute. 1 minute.
Okay.
Okay, sir, done.
Okay. Okay, now a couple of more practice examples for just calculation of tension we will see, and then eventually we will come to systems which have pulleys, etc. So this is very straightforward standard type of problem. So we have a combination of two blocks like this, which are attached like this. So A and B are of masses 5 kilograms and 10 kilograms. Both threads are massless, basically very light. So find tensions T1 and T2. Okay. Very straightforward question. People just try this out quickly and send me the answers. Yes, very good, Sanvi. That's correct. Yes, Ayush, that's correct. Yes, Rishita, correct. Okay, so basically, as you would have all understood, all you have to do is make the free body diagrams of A and B. Problem cannot get easier than this actually. Solving these, you can see that T1 is the combined weight Now there's one more thing you can do here. Another option. Optionally, what we can do is make a combined free body diagram for A plus B. So, treat this like A plus B. It's okay. So on this, there's a combined weight active. So this equation comes directly. So sometimes it's useful to make a combined free body diagram. No, so that is the point, beta. What you have to understand, Kushi, is that on the block B, okay, who is applying force? Which all objects are applying force on it? It is attached with the second thread, so T2 is acting on it. But is the block B attached with the first thread? No. So T1 is not acting on it. And the other thing is that the earth is pulling B down with a force equal to its weight because of gravity. So on the block B, there are only two forces acting. One is the earth is pulling it down with a force equal to its weight, and the other is at this point where the string is attached, the string is pulling it up. But T1 is not there on this, okay, because this string is not in contact with this one. T1 acts on A. On A, you can see that there is this string pulling it up, this string pulling it down, and its own weight. Okay, so hope it is clear, which is why T1 will not figure in the free body diagram of block B. Only figure in the free body diagram of block A. Right. Okay, very good. Now let's look at a problem where we combine some of the concepts that we've learned in the last lecture with today's lecture. So let's say we have this smooth inclined plane of 30-degree inclination. And what we've done is we've taken a combination of two blocks, A and B, but they are attached by a light thread. Now we are applying some force on them such that the system accelerates up the inclined plane at P. So suppose given that mass of block A is 6 kilograms, mass of block B is 4 kilograms. We have to find F and the tension T in the string or in the thread if the acceleration of the inclined plane is 2 meters per second square. I can take G as 10 meters per second square. Try this out. So also make free body diagrams of E and B to calculate the normal reaction on each. Yes, Sanvi, your answers are correct. Yeah. If anybody else has also got the answers, please send them to me. So see that it's a light string, so tension will be acting like this. So now this is where the concept of free body diagram becomes very important. For example, if you see on the block A, the forces acting are its weight, tension T, and normal reaction like this, giving it an acceleration in this direction. Similarly, if you see the block B, the forces acting are the external force acting parallel to the inclined plane, tension, normal reaction, and weight. This angle being theta, here these angles are theta. So if I draw the resolved free body diagrams for each of them, I'll see for block A, there's normal reaction, tension, and components of weight. Mg sine theta, similarly for block B, these will be the force diagram. Okay. So taking this as our x-axis. For the block A along the x-axis, the block B along the x-axis, you can just add the two equations. Something like this. Okay, so just follow the language of the free body diagrams and corresponding equations very carefully. Make sure you understood the resolution of the forces and all that, and also find the other two things here, which is the normal reaction acting on A and the normal reaction acting on B. That's directly there in the diagram in front of you, so you can work it out quite easily. Also, you have to calculate the tension in the string. So same equation, but you have to substitute and find out the tension also.
So वो F के नीचे क्या लिखा है? So
Okay, so let's wind this up, people. So this now we can see that substitute this the first equation. Okay.
So wait, it was not done.
Okay.
Done, sir.
Okay. Now the next thing we'll see is pulley. So in this chapter, we will be studying a type of pulley which is called a smooth and fixed. Pulley. So typically, the diagram of a pulley might be shown as something like this, where either the pulley's axle is attached like this to a fixed ceiling, or the pulley might be attached to a surface like this, whatever be the case. So the three-dimensional proper structure of the pulley be that it's like this. Now, a smooth fixed pulley means that this surface of the pulley is a smooth surface. That means any thread can slip freely on it. And fixed means that this axle, this is a fixed axle. So it is a non-rotating pulley. So that is the type of pulley that we study in this chapter. Rotating pulleys is something that we're going to study in a later chapter. That will be discussed in a later chapter called rotational mechanics. You know, it's a very simple example. Suppose we have a situation where pulley is attached to a ceiling like this here, and a light thread goes around the pulley like this. Now one end of the thread is attached to a block like this, and the other end of the thread is being pulled with some external force like this. So given that the mass of the block is 5 kilograms and G is equal to 10 meters per second square, you want to find the tension in the rope or the thread and the acceleration of the block. If the external force you are applying on the thread, that is exactly equal to, let us say, in the first case 50 newtons, the second case 70 newtons, and in the third case say 50 newtons. So let's work out this question next. First, you can just write down this section about
So,
pulleys. Yes. Yes, beta. You wanted to write this down?
yes, sir.
Yeah. Okay, so let's understand the situation here. So this might be a little bit unfamiliar in the beginning. So we'll just relate it to what we've learned about threads and tension in a thread, that kind of situation earlier.
So could you please scroll up?
Yeah.
Use the writing pad.
Okay. The earlier part of the question.
Such a little bit of the above.
Okay.
Okay, sir, done. Only the example. That's
Okay. Now see in the example, first of all, what we'll understand is that the weight of the block acting on it gives it a tendency such that the block is pulling downwards on the thread. And from the other side, we are applying external force. So the combination of these two things happening, that is gravity pulling the block downwards and the external force pulling the end of the thread on this side in this direction. So one is that mg is pulling on the block downwards, and the other is the external force. So the combination of these two things means that the string is kind of stretched out. So it develops a tension which acts in this manner. And it's a massless thread, so the tension is uniform throughout. So this kind of thing happens. Next, what we do is we can make a free body diagram of this end P, FPD of the end P of the thread. So regardless of whether it's accelerating or not, the end P is a massless point. Okay, because the thread is massless, so it does not have any mass. So the net force on such a point must always be zero, because F is equal to ma and m is zero for that point. So this is a massless point. So the net force on it must be equal to zero always. So that will tell us that the tension in the thread develops a value equal to the external force that we are applying. So now depending on, so now next when you look at the free body diagram of the block, you'll understand that the tension in the thread is equal to the external force that we are applying. So if the external force is greater than mg, then the block will accelerate upwards. If the external force we are applying is less than mg, then the block will tend to accelerate downwards. And of course, in the special case, if F external is equal to mg, so the tension in the thread is equal to mg, the acceleration of the block will be zero. So now you can work out each of the cases from this. So if it is a case like this, it's case B. If it is this case, case A. will have a downward acceleration of 4 meters per second square. So this is an example of, a typical kind of system where we are making use of a pulley. So in a practical situation, you can understand like this, that the advantage of using the pulley is that we can use a horizontal force to ultimately pull a block upwards, or even to, gradually let it go down, but with an acceleration less than g. Suppose we are in a situation where we want the block to move along a vertical line like this, either upwards or downwards, but for whatever reason, it's not convenient for us to apply a vertical force on the thread. It's more convenient for us to orient the thread horizontally and then apply a force horizontally on it. So we can use a pulley over here, which bends the thread in between by 90 degrees. So even though a horizontal force is applied at the end P of the thread over here, that horizontal force is generating a tension in the thread, and ultimately through that tension we are able to apply a force vertically on the block. So this becomes like a very basic building block of any mechanical engineering system, because you want to always change the angle at which the force is applied versus the force is acting on some body. So a pulley and thread system or a pulley and chain system can be used for that.
So could you please roll up a little bit of the question? I missed out some.
Okay.
Okay, sir. Thank you.
Okay. Okay, so make sure the equation solving part is clear. Okay. I've done the final calculation over here for ABC part. Okay. So ultimately you can see, regardless of whether the block is being accelerated upwards because the tension is exceeding the weight or vice versa, the tension in the string will be exactly equal to the amount of external force applied at the end P. Whatever force you apply, that will become equal to the tension.
Sir, if in the question only tension is asked and nothing else is written, so we have to directly take the weight of the block, no?
Nee, weight of the block nahi beta. This is what I'm trying to explain. The tension is determined by the external force we are applying. Okay. Weight of the block वो tension के comparison में कितना है, that tells me whether the block is accelerating or not. You understanding my point, na? In
Okay,
all
sir,
the three
understood.
cases ABC, na, the weight of the block mg is the same. It's 50 newtons. But in one case, I'm applying the force of 70 newtons. So tension is more than weight. So the block ends up accelerating upwards. Okay. Now suppose we had a situation like this, that at this end there is a wall like this, and what I've done is I've just attached the thread to this point on the wall like this, and the other end of the thread. Now obviously in this case what would happen, that the tension in the string will automatically become equal to the weight of the block, because its acceleration will be 0. So यहाँ पे the tension is decided by the weight of the block. But this is different to this case, because here the tension is generated by the force. So T would be equal to mg in this case. Okay. But in this case, we are controlling the tension by applying a force here. So we are able to control whether or not the block accelerates.
Okay, sir, understood.
Understood? Okay. So we will conclude today's session here. So we will spend like a couple of lectures now, the next couple of lectures discussing various systems which have pulleys and threads like this. Okay, so we will see systems like the one here where there's a single pulley and a single thread going around it, and gradually we'll come to more complicated situations where we'll look at in the next session and onwards. We'll look at systems of pulleys. Okay, and those kind of situations. So you can now, yeah, I will also be sending a separate worksheet for this, as well as from HC Verma you can work out questions. Okay, from HC Verma, Newton's laws motion chapter, you can work out questions in the main exercise. At the end of the chapter, the main exercise, you can work out questions 1 to 16. In fact, you can work out questions 1 to 22. You can also go through the solved examples. One to 8. Okay. Plus, I will be sending a worksheet across. You can start doing questions from that also. So next lecture, we will also discuss some of the questions from HC Verma. Specifically also if you have any doubts in any of those questions. So that's it for today's session, people. Thanks for attending. Wish you all the best.
Thank you, sir.
Okay, bye.
Thank you, sir. Bye, sir.
Thank you, sir.
Sir, can you send a photo of those questions?
The HC Verma questions.
Yes, sir.
Okay, just send me a text message later. I will send you a
Okay,
message.
sir.